So the first talk is going to be by Alex Tovbis from Orlando, from the University of Central Florida. He's going to speak about some recent developments in spectral theory of soliton gases for integrable equations.
Thank you, Peter. I want to thank the organizers of this program. It's a continuation of the program in Isaac Newton Institute 2 years ago. It was a great event, and I'm happy to be here. So I thought that I will talk about, not again repeat what I told at the seminar, but rather talk about my recent paper with Fudong Wong about the circular gas. So rather, it's not a circular gas, it's rather circular condensate. And if I want to draw occasionally something on this whiteboard, I can use this, right? Okay. So we're considering, so my interest in the soliton gas for focusing on linear Schrodinger equation. Here is focusing on linear Schrodinger equation. There's a Lux pairs. I think the subject was mentioned several times, so I will just and this information is mostly known, so I will just skip and go to the next slide. So again, that's focusing on linear Schrodinger equation. These are distinguished solutions, like a plane wave or a soliton with initial position and initial phase. Then there is a Peregrine breather, many other type of breathers, and in soliton gas theory, we understand gases as randomized large ensembles of special solutions, which we treat as quasi-particle. Okay, so let's go straight mathematically. What does it mean? So for soliton gases, uniform and not uniform, nonlinear dispersion relation, and this I remember in the other language is thermodynamic beta andas, I hope that's right, which defines the density of states U of z and its temporal analog density of fluxes V of z are just these two integral equations. Okay, so we need to figure out what is the input data for that, and so that's pretty clear. So the input data is the spectral scaling function sigma. In the case when sigma equals to 0, we call it condensate, and you will see some special limit of gases. And the other piece of information is gamma plus, which is a compact in the upper complex half plane. And I forgot to mention that the Zakharov-Shabbat spectrum for focusing NLS equation is Schwarz symmetric. So therefore, considering only upper half plane is sufficient for our purpose. So this is the object that we would like to study, like what solutions it has, existence and uniqueness, and other particular examples. There are many questions related. There is also observation, but we also want to see some observable. So if we call something a soliton gas and we want to model it in experiment or in numerically, we want to see something, look at the picture and identify something. So one of the simplest things is to take a ratio V over U and call it effective velocity of a tracer. And then it is clear that if you connect V and U through this function S, so the function S will, a simple manipulation with these two equations, linear combination of these two equations, will give you produce this equation, which is called the equation of states, where S0 is the speed of a free solid. Right, and S is unknown, and S is unknown effective velocity. So in this equation, we sort of assume that if we know density of states, then we can, by solving this equation, perhaps we can produce effective velocity of the solid. And it is also clear that if we know that the support gamma plus does not, so we can additionally, so what I said is the is the gas uniform gas, which is the same in all x and t, but we can allow on large scale of x and t to be different, and then on the large scale we have the second equation, the differential part, which is called together this and this, Gennady called in the KdV context called kinetic equation, right? And from this kinetic equation, if we assume that gamma does not change with x and t, we immediately can conclude that sigma, which Benjamin called occupancy, one over occupancy number or something like that, that's how it evolves with x and t. Okay, so just a little observation that if we replace minus z bar with z in this kernel and adjust the right hand side here in the second equation, we get equation for the soliton gas nonlinear dispersion relation for KdV. Okay, that's just good to know. And now how we can observe the effective velocity. For example, on this famous slide from 2016 paper, we see that there is a gas, and then there is a soliton that perhaps not element of this gas, but you can think it to be element of this gas. And as it starts moving through the gas, so after some time, that will be the position of the free soliton, but this is the actual position. So this discrepancy allows us to visualize this, to have something observable, the effective velocity. So we can now ask many questions, for example, about rigorous derivation of nonlinear dispersion relation, existence and uniqueness solutions, special cases, statistical descriptions, soliton gas for various integrable system, and so on and so forth. Of course, I don't attempt to answer or even mention all of them, but just some. So one example is a bound state condensate for NLS. That is when we have gamma like. So because of the Schwarz symmetry, I sometimes use gamma, sometimes use gamma plus. Gamma being this gamma union complex conjugate. So that is for this condensate, right? So the gamma is here shown, and so Q is IQ and minus IQ are these 2 points, and sigma is 0. We have a condensate. So U is pretty simple. V is just 0 because it's a bound state. So everything is more or less clear, and you can disregard whatever else is written here. Let me give. So that was a bound state condensate. Another example is a non-bound state condensate. So again, at the bound state condensate, the velocity of each element of the gas is the same. So that's why they bound. Right, in this situation, they're all different, right? So that is example of a circular gas when we have the circular condensate when gamma is like that. And so here it's 0. Gamma is something like that, and this point and this point. So there is a point Z1 here and Z1 bar, and this is, I don't know, rho. Let me take 1, or maybe it's rho here. So that's another example, and you see again solution. Now V is non-trivial, but still can be written, and U also can be written in terms of geometry of this configuration, and this effective speed also can be written, and the curious observation is that if you can move this point z1 to the end to -1, then this velocity, the effective velocity will be that, which is double the free speed of a free solid, which is somehow I don't think I understand, or if anybody understands this, I would be glad to know why it is double. But that's the fact that formula tells us, and that's a picture of this soliton condensate produced by Stefan, I think, Stefan Randu. Okay, so now I want to briefly touch the question very briefly, or how we derive this integral equations, where they are coming from. And again, trying to be light without much details, we assume we take approach, so we consider thermodynamic limit of finite gap solution. So that means that we have a hyperelliptic Riemann surface with blue bands shown here as a branch cut. And given this surface, we can have family of solutions of finite gap solutions to the focusing nonlinear Schrödinger equation defined by this Riemann surface up to initial phases. But we don't, so we don't look at particular, solutions. Therefore, we are not paying attention to additional to the phases. So then we have A cycles, B cycles as usual, as shown here, Schwarz symmetry. And on this Riemann surface, then the next step. So Riemann surface is here. The next step, we introduce objects, uniquely defined objects on the surface called quasi-momentum and quasi-energy differentials. So these are differentials that are uniquely defined by the following properties, but by their asymptotics at a singular point at infinity on both sheets, and by the normalization. And normalization is real normalized. So we assume that all the integrals of any closed loop is zero, right? I'm sorry, the imaginary part is here. They're purely real. That's why they are called real normalized. Okay, and so there is it is well known that they are uniquely defined by the Laurent parts at singular points and real normalization. So we then calculate the periods of these differentials over A and B cycles shown here, and we identify them with the case with wave numbers and omega with frequencies. That's our interpretation, what they are. Okay, and then the question, okay, what connection do we have between these quantities? And that is provided by Riemann Bilinear Relations that given a pair of differentials, right? So the periods are connected. And so one differential is, so this is a Riemann Bilinear relation. And for example, take as one differential, take either dPn or dQn, and as another differential, take this basis of holomorphic differential, normalized basis of holomorphic differentials, and then you get the genus is 2n in this case, and then you get 2n equations for these wave numbers, and another 2n equation for frequencies. So in a sense, that is the nonlinear dispersion relation. Nonlinear dispersion relation is in discrete case. So I was very interested in listening to Zhenya today, where he talked about how you take these integral equations and discretize them and see what happens. So it's sort of this discretization perhaps is approximated by those when n goes to infinity, and it would be nice to understand a little bit better the connection, if any. Okay, so now what is so? By the way, please let me know if I'm jumping too fast over the stuff. So in particular, so this differential omega j, it has this form, polynomial divided by the radical. Radical is here. There are all branch point. Polynomial is uniquely defined by this normalization condition over A cycles. This is uniquely defined object, so the system is uniquely defined. Well, how many equations, if we take this one, how many equations we have? Well, we have 2n equations, and how many unknowns we have? We have 2n unknowns, so everything is good. And they can be easily separated using the fact that it's real normalized differential. So if you take real part, if you take, I'm sorry, imaginary part, you see this guy cancels out because they're real. And so then we got this equations, if we take only imaginary part. And then if we take real parts, we get the other. So we call it the solitonic wave numbers and frequencies and carrier wave numbers and frequencies. These two corresponding to two different equations. Now I've heard Benjamin talk this morning, and I'm not sure if that falls into the category of additional dimension that Benjamin mentioned. Probably not, but I'm not sure. Anyway, so these equations sort of were known going back to the Flaschka-Forrest-McLaughlin paper of 1918. So the first one, but not the second one. The second seemed to be, at least I don't know where else they were considered. Yes.
So this Riemann Bilinear identity is not, you use very specific differentials to get these equations, but you could use any combination of differentials.
Yeah, of course. So far I use particular differentials, but
So do you
in
obtain
principle,
interesting equations?
What?
Do you obtain new interesting equations by?
using other differentials. Well, so far these are the differentials one can use, and the only thing that there are higher times, and of course then you can use easily understand which differential you use and do that, or take linear combination of flows and all that. Yes, yes. Okay, so now we are back. So now you see, so in the so how do we obtain the integral equations? So you have to go to the large n limit of this system of linear equation, where now the bands and gaps should be chosen in a special way called thermodynamic limit, and to be able to make transition from these equations here to this integral equation. Okay, I have to, because of the lack of time, I have to skip it completely. Details. You can ask, okay, can you prove that in that limit, the discrete equation, the system of linear equation give you this integral equation? So far we were able to do it with Sedong, assuming that sigma is strictly positive. Right, then after under these conditions, we were able to produce an argument showing that indeed there is a conversion. If sigma is strictly zero, so condensate case, I believe that is also possible, but I don't know the proof. And not to mention when sigma somewhere zero, somewhere not zero, that's a hard situation. Okay, so now let's go to the question. Okay, but if you have a equation, how do you know that solution exists, is unique, and so on, and so forth? So this can be answered in the following way. So it's a solution of integral equation, Fred-Kolom integral equation, but because sigma can be positive, can be zero, can be, the existence uniqueness is not absolutely clear. So this question can be answered in the following way. That's my paper with Arno Koolars in 2021. So when we introduce the energy function like that, so here G is, so any of these equations can be written as Green's, so that's G of U is this integral part. or it's called Green's potential of measure U. And so then if we understand that G of U is that, then we can introduce the energy as mentioned here. And then we prove that there is there is a unique and if we want to minimize this energy functional in the among all positive absolutely continuous Borel measures, right? Then the answer is yes, there is a unique minimizer of this sort. And if we assume additional conditions about how nice is sigma and how nice is phi, then we can show that. So this equation, which is one of the nonlinear dispersion relation, will be then Euler-Lagrange equation for this functional, and we can show that it has the minimizer satisfies this equation at every point. So that means solution existent and is unique and positive for on the support gamma, subject to some additional conditions that written there, but I'm not paying now. I will not spend time on that. So okay, I think I have to accelerate. So this slide shows that the condensate is, if you fix gamma and phi but start to play with sigma, the condensate will give you the largest average intensity of the gas. Okay, and now we want to I want to go to the probably I should skip about KdV condensate and go about circular condensate. What is that? So when you have this circle, as I put here, but instead of one arc as support, you have a number of arcs here. And in this case, and of course in lower half plane symmetric. In this case, again, one can solve the problem explicitly, find solution of this integral equation. And the key is to realize that this Zhukovsky transformation maps the upper half plane into the complex plane cut around this bands, right? So so in the new plane we define gamma plus hat. So if this is gamma plus here, the gamma plus hat is there. And of course, because of this transformation has a singularity, we have a branch cut from -infinity to -1 and from 1 to infinity. Okay. So, and then if we denote by U hat solution of this or inversion of this Hilbert transform on this intervals, this and that. And so it is known to be, it's known to have this form polynomial divided by the radical. Polynomial, and for V polynomial divided by this radical. But this transform is not uniquely defined because the kernel is non-trivial. So there are some additional conditions are needed to normalize it. And so I would say the main theorem says that the density of states and density of fluxes are given with this formula P, this polynomial over radical of the Zhukovsky transformation, and the same Q polynomial of the radical of the Zhukovsky transformation, where this kernel is defined by this set of conditions. So integrals over the gaps are here, right? Integral over the gaps should be 0, right? That's uniquely defined condition. And you can say what happens if the gaps like touch the real axis, then this integrals just goes into requirement that the value of U at this point +1 or -1 becomes 0. Okay, so in particular, that is genus 1 solution. If so, this is genus 0. So we have 1, 2. So the genus is the number of gaps in this situation, right? So this is genus 1 solution, and if you take A3 equals 4 as here, then it's genus 0, and the formulae are here, and the velocity is here, and these are the results we got. And for more general genus, the elliptic function started to play a role, and we got the expression for solutions. They are now modulation equations. Well, modulation equations, as we know, should look this way, right? And so we can show that if you allow this slow modulation, the points, the end of this interval will slide along the circle, and they satisfy this Witham type equations, where Vj of alpha has this expression. Okay, and then we consider, so because my time is coming to, excellent. Okay. Yeah, so we can consider the Riemann problem. For example, we say that we have initial data on the Riemann problem on the contour. We said that for at time equals 0 for positive axis, we have this band, for example, and for negative axis, we have either larger band or slower band. Because it's condensate, bands defines everything, right? Solution is defined by the band. So how would evolution go in this case? So we have again the example of rarefaction way and the dispersive shock way. The rarefaction way. So these are some. So this is the equation for the motion of the endpoints, which you can be written this way and solve. And you see these pictures show that this is the rarefaction way of this condensate, and this is dispersion shock way related to that. And we calculate again all the quantities of interest. And this is for the dispersion shock wave. Now this is the equation, and solution can be again explicitly calculated. And so these are two velocities, v2 plus and v2 minus. Okay, so let's go now one more subject I wanted to touch is the kurtosis related to this equation. So kurtosis is, as it was mentioned today several times, it's a normalized force moment that we can express in terms of average conserved densities and average fluxes. Conserved densities are I, conserved fluxes are J. Here J are non-trivial because it's non-bound state.
Angle brackets are this.
What?
Angle brackets, integrals.
I'm sorry.
Average.
Yeah. There are average. Right. You're right. Over here, yes. And so we have expressions for in terms of density of states. We have impressions for that here and here. And so the calculation again shows that these quantities can be expressed in terms of the solutions U and V, and also J's Chebyshev polynomial of the second time, this UJ's. And moreover, we can show that in the case of a rarefaction way, the kurtosis is always 2, right? And in the as shown here. And in the case of dispersion shock wave, situation is a little bit more complicated. Namely, the kurtosis kappa for the focusing nonlinear circular condensate is given by, so you have A1, A2, these points, right? A1 and A2. And so the kurtosis is given by this expression where the numerator is a little bit of complicated formula. M is this quantity, mu is this quantity. And from this formula, it follows the kurtosis should be between 2 and infinity. 2 can be included. So I think it's a typo here. It should. So and we can also derive here that kurtosis for genus 0 condensate is always 2. What happens if so again? I'm sorry for that. And so the interesting situation happens. The interesting situation happens when we want to calculate kurtosis in this angle. Then one can show that depending how you approach this point, kurtosis can take any value greater than 2, greater or equal than 2. Okay, with this, I thank you for. Yeah.
Question for Alex.
Yes.
This fancy shock wave, how do you compute the wave is using, you would use Riemann with your data?
We have exact formula. You mean this one?
No, but this is just, I mean, you expect that the wave will break into the different liquids, no? That's what it's.
This shows how the branch points move. Yeah, this is just branch.
Then you need the.
Yeah, it's not in the physical space. So this is a motion of branch point, and then we calculate density of states color coded here. This like evening sky or whatever, morning sky is a color coded function logarithm u1.
It's semi-question, semi-color, you already mentioned it. But I find it really non-trivial, it is there that they characteristics the real additive focusing analysis. So these are not with the original with the equations. I mean, these are clearly modulation equations, but I'm not sure you can obtain them by averaging analysis. That's why it's highly really.
Alex, have you tried to look at other simple wave solution? I mean, for instance, for one where you will get like for KdV, where you will get because here the band. Oh no, you could stay on the. So go back to the plot. Because here for the dispersive shock wave is lambda is your second Riemann invariant that is moving. But have you tried to look at if the third one or the first one are moving?
No, we assume that these are constant. We didn't try this.
Okay, so you did genus 0,
Yeah,
genus 0.
yeah.
All right.
Well, we certainly can do it if.
Yeah, I mean you have all the equation.
Let's thank Alex again.